Find somewhere comfortable tonight. Wherever you are, lying down, curled up, somewhere quiet or somewhere almost quiet. You don't need to follow any of this closely. You don't need to hold on to it or remember it in the morning. These are just words riding softly in the dark, and you can let them pass through you like a slow tide. Tonight we are going somewhere very far away, not in distance exactly, but in time, further back than the first stars, further back than the first galaxies, back to a universe that looked nothing like the one outside your window, a universe without atoms, without transparency, without any light that could go anywhere at all. It is a story about how something as simple and ordinary as a single atom of hydrogen came to exist for the very first time. And it is a story about light, light that has been traveling since before the earth was formed, before the sun was formed, before any star had yet ignited in the dark. Light that is, right now, this very moment, arriving here. You don't need to concentrate. You don't need to do anything at all. Just let the words settle over you, the way the dark settles over a room when someone gently turns down a lamp. We are in no hurry tonight. We have nearly 14 billion years to move through and all the time in the world to do it. There was a time, and this is not a metaphor, this is the actual history of everything, when the universe contained no atoms at all. Not a few atoms, not rare atoms, none. The whole of existence, every particle and every flicker of energy existed in a form so different from anything we encounter in ordinary life that it takes a while to even approach it with the imagination. Picture the densest, hottest, most violently energetic thing you can. The inside of a star, perhaps that churning, roiling furnace where temperatures climb so high that nothing solid could survive for even a fraction of a heartbeat. Now imagine something hotter than that. Far hotter, hotter by such a vast degree that the comparison barely holds. That was the early universe, not in one place, everywhere. All of space, in every direction, filled with the same furious, blazing substance. And in that substance, two kinds of particles mattered most to the story we are telling tonight. The first is the proton. A proton is a tiny thing, almost impossibly small, carrying a positive electrical charge. It is what sits at the heart of every hydrogen atom in your body right now. Though in those early moments, it was not inside any atom. It was alone, free, tumbling through the heat. The second is the electron, even smaller than the proton, carrying the opposite charge, negative, where the proton is positive. They are drawn to each other. These two, the way opposite ends of a magnet are drawn together. Given any piece at all, a proton and an electron would find each other and settle into a quiet partnership, the electron curling into a gentle orbit around the proton, the two of them becoming something stable and whole, a hydrogen atom. The simplest thing the universe knows how to make. But there was no peace, there was no quiet, there was only heat. In those early moments, the universe was so hot that light itself was a weapon. Not light as we think of it, the warm glow through a window, the soft lamp beside a bed. This was light as raw energy, photons carrying such enormous force that any time a proton and an electron drifted close enough to touch, a photon would slam into them and tear them apart again. The attraction between the two particles was real. The pull was genuine. But the violence of the surrounding light was simply too great. Every attempt at union was immediately undone. This is the first strange thing to sit with. Light existed in the early universe. Vast, overwhelming quantities of light. For every single particle of matter, there were roughly 1 billion photons. 1 billion. The universe was almost entirely made of light in terms of sheer numbers. And yet that universe was completely, utterly dark, not to any eye that might have been there, but in the sense that none of that light could go anywhere. Think of trying to see through a thick fog, Not a morning mist that softens the edges of things, but a fog so dense that a torch held at arm's length would vanish into white within a few inches. The light is there. It is real, but it cannot travel. It is scattered and deflected and absorbed before it can carry any information, any image, any sense of the world from one place to another. The early universe was like that fog, except the fog was everything, in every direction, with no edge and no clearing. The reason was those free electrons. An electron, when it is floating loose and unattached, is extraordinarily good at interrupting a photon. A photon moving through a sea of free electrons does not get far at all. It travels a tiny distance, smaller than anything we have a comfortable word for, and then it collides with an electron and bounces away in a new direction. Then it travels another tiny distance and collides again, and again, and again. The photon is not destroyed, it is just perpetually interrupted, perpetually redirected, going nowhere in particular, trapped in the fog of its own endless deflections. This is what the universe was for a very long time, a place of extraordinary energy and extraordinary opacity, a place where light and matter were so thoroughly entangled with each other that they moved as a single substance, a single churning whole, where the protons wanted to find their electrons and could not, where the light wanted to travel and could not, where everything was in motion and nothing was going anywhere. It is a strange kind of existence to contemplate, not dark, exactly. If you could have been there, the glow would have been overwhelming, a blinding, burning, orange-white radiance in every direction, like standing inside the surface of a star with no escape, but not transparent either, not open, not free. The universe, in those first hundreds of thousands of years, was a place waiting, without knowing it was waiting, for something to change, for the heat to fall, degree by degree, to a point where the light would finally loosen its grip on those wandering electrons, for the fog to begin, at last, to clear. That clearing was still a very long way off, and the waiting, as we will find, required a patience almost beyond imagining. The universe was cooling, but slowly, with a patience so vast it barely registers as a process at all, more like a condition, state of being, an almost geological stillness in the rate of change. From the very first moments, the expansion of the universe was carrying everything outward, and as things spread out, the temperature was falling. This is a familiar enough idea in a quiet way. When air expands, it cools, which is why a breeze from a fan feels cooler than the still air in a room. The universe was doing the same thing, on a scale that swallows all comparison, expanding in every direction simultaneously, cooling as it went, the temperature dropping from the unimaginable heights of its earliest moments towards something lower, something quieter, degree by immeasurable degree. But the cooling was not fast, not by any ordinary measure of time. Picture a vast forge, one of those old iron foundries where the walls themselves glow orange with stored heat, where the air shimmers and the metal holds its warmth for hours after the fire has been banked. Now imagine a forge the size of everything, a forge with no walls, no outside, no cool place to radiate its heat toward, a forge that is simply hot, uniformly and completely, with no room left in existence for cold. That forge would take a long time to cool, a very long time. The universe needed nearly 400,000 years. 400,000 years of gradual, patient, imperceptible cooling before the temperature fell far enough for anything to change. 400,000 years during which the protons and electrons continued their endless, frustrated dance, drawn together, torn apart, drawn together again, over and over, in a cycle that never resolved. The heat kept winning. It kept winning for so long that if you compressed the entire current age of the universe into a single calendar year, those 400,000 years would occupy only about the first 10 hours. A brief morning in cosmic terms, and yet, measured in any human scale, an incomprehensible expanse of time. The key question, the thing that determines everything about when the change finally came, is not simply about temperature as an abstract number. It is about a specific competition, a tug-of-war between two forces, and what happened when one of them finally began to lose. On one side of that contest, the pull between a proton and an electron, opposite charges attracting each other. The deep, patient, built-in tendency of the universe to bring these two together into something stable and whole. This pull does not change with temperature. It is simply there, constant, the same at any heat. On the other side, the energy carried by the photons of light surrounding every particle. In the early universe, those photons were so energetic that when a proton and electron managed to find each other and begin to settle into partnership, a photon would strike almost immediately and give the electron enough of a kick to escape. The partnership would dissolve before it had properly formed. The proton would be alone again, the electron tumbling away into the plasma. This happened over and over, trillions upon trillions of times, across the entire cosmos, continuously, for hundreds of thousands of years. The forming and the unforming, the joining and the separating. But the photons were losing energy as the universe expanded, very slowly but consistently, each one carrying slightly less of a punch than before, and there came a point, not a sharp moment, not an instant, but a threshold, a zone of temperature, where the photons were no longer quite energetic enough to do the job, where the kick they delivered to an electron was no longer sufficient to tear it free from the proton it had just found, where the attraction was, at last, stronger than the disruption. This threshold arrived when the universe had cooled to something in the region of 3,000 degrees, which sounds hot, and by any human standard it is incandescent, far beyond anything we encounter on the surface of the Earth. But compared to the millions and billions of degrees that had come before, it was a kind of coolness, a relative peace, a temperature at which the light, finally, was gentle enough. It is worth pausing here to appreciate just how specific this threshold was. The physics of the situation required the temperature to fall to a very particular range before neutral atoms could survive. Too hot and they were ripped apart. Too cool. Well, there was no too cool. The atoms, once formed, would endure. But the window between the heat that prevented formation and the quiet that allowed it was not arbitrary. It was determined by the precise strength of the attraction between a proton and an electron, and the precise amount of energy a photon carries at a given temperature. These numbers are what they are, built into the fabric of the universe, and they combine to set the clock for that long, slow wait. Something else is worth knowing about what formed when the wait finally ended. The universe by this point was not made of exotic, complicated stuff. The processes that had happened in the first few minutes after everything began had already determined what kind of matter existed, mostly the simplest possible ingredient, the building block of all building blocks. One proton, one electron, nothing more. Hydrogen. There was also a smaller portion of helium, atoms with 2 protons and 2 electrons, slightly more complex, slightly heavier, and traces of a few other light elements. But the overwhelming majority of the matter in the universe, as it approached that critical threshold, was going to become hydrogen. The same hydrogen that makes up most of the sun. The same hydrogen that combines with oxygen to make the water in the glass on your bedside table. All of it waiting. All of it, across the entire vast cosmos, poised at the edge of a change that 400,000 years of heat had been holding back. When the temperature fell to that crucial point, what happened was not a single event, but a wave of events, a cascade of joinings happening simultaneously across the entire universe, each one quiet and small, each one the same as the last, and each one a kind of miracle in its own right. An electron, drifting through the cooling plasma, encounters a proton. The attraction between them is real, and now the surrounding light is no longer violent enough to intervene. The electron begins to settle. But here is something beautiful about the way this happens, something that is easy to miss if we think of it as a simple snapping together of two pieces. An electron does not simply fall inward and stop. It does not drop directly to its final resting place in a single movement. Instead, it descends in stages. It finds a high outer orbit first, a wide, loose, distant relationship with the proton at the center, and it stays there for a moment. Then it drops to a lower orbit, then lower still, then lower again, until it reaches the innermost, most stable position, the quiet place closest to the proton where it will remain. And at each step of that descent, something is released. Each time the electron drops from one orbit to a lower one, it sheds a small packet of energy, a single photon released into the universe. A tiny burst of light, specific in its color and its energy, the precise amount corresponding to the distance between the two orbits the electron has just traversed. Drop by drop, step by step, the electron gives up its extra energy on the way down, like a stone finding its way from ledge to ledge, down a cliff face, releasing a small sound at each impact. This is one of the quieter wonders of the physical world, that the journey of an electron to its final home is not silent, but announced, each step marked by the release of a particular color of light. Different steps produce different colors. The whole sequence has been studied and mapped, and each transition has its own precise signature, its own wavelength, its own note in what you might think of as the spectrum of a hydrogen atom finding itself for the first time. Now, this process, an electron cascading down through a series of orbits toward its final resting place, could only happen once the light surrounding it had grown gentle enough. In the earlier, hotter universe, even if an electron managed to drop to a lower orbit and release a photon, the photons in the surrounding sea were so energetic that they would immediately be absorbed by another nearby atom, kicking its electron back up to a higher orbit. The whole process would be undone almost as quickly as it happened. The light was too active, too disruptive, too present. It kept everything stirred up. But as the temperature fell, the surrounding light became less capable of this interference. The photons released by cascading electrons could travel a little further before being reabsorbed. And gradually, the balance shifted. More electrons were completing their descents and staying put than were being kicked back up. The process was becoming, for the first time, irreversible. And then it happened everywhere at once. Not instantly. The transition took several thousand years to complete, which is swift in cosmic terms, but not a single moment. Across the entire observable universe, in every direction, at roughly the same time, the same process was playing out. Electron after electron finding its proton, cascade after cascade releasing its small gifts of light, atom after atom coming into stable existence for the very first time. The numbers involved are difficult to hold in the mind. For every grain of sand on every beach on Earth, multiply that by a number large enough to fill an ocean, and you are still not approaching the count of hydrogen atoms that formed during this period. Billions upon billions upon billions, each one a tiny private joining, each one the same fundamental event, a proton and an electron becoming, together, something new. There is a curious thing about the name that physicists give to this event. It is called recombination, as though the protons and electrons were reuniting after a separation, coming back together after having been apart. But this is not what happened at all. These particles had never been combined before. There was no earlier time when they had been joined and then separated. This was not a reunion. It was a first meeting. A first and only meeting between particles that had spent the entire previous history of the universe in the same hot, churning space, close enough to feel each other's pull, never quite able to stay. The name is a historical accident, a word chosen before the full picture was understood, and it has stayed in the language the way old words do, not because it is accurate, but because it arrived first. What it describes, if we set the misleading prefix aside, is simply combination. The universe, for the first time, combining its ingredients into something stable, something whole, something that would endure. The atoms that formed in those thousands of years have been atoms ever since. The hydrogen in the water you drank today contains protons that were present in the plasma of the early universe, waiting through all that heat and time for an electron to finally stay. The waiting, in the end, was worth it. Something changed about light itself. Not about what light was, or how fast it moved, or the nature of its energy. What changed was simply this. For the first time in the history of the universe, light could go somewhere. Before the atoms formed, every photon in existence was a prisoner of the fog, deflected and scattered by free electrons so continuously, so relentlessly, that it could not travel any meaningful distance in any direction. The universe was full of light and yet impenetrable to it. A photon born at one location would never reach another location in any useful sense. It would spend its existence bouncing endlessly through the plasma, going nowhere, carrying nothing, like a message sealed inside a box that could never be opened. But as the electrons found their protons and settled into atoms, the fog began to thin. A neutral atom, a proton with its electron properly orbiting, the two charges balanced and contained, is a very different thing to encounter from a photon's perspective than a free electron is. A free electron is highly reactive, highly interruptive. It catches photons easily, deflects them readily, is always ready to absorb and re-emit. But a neutral atom, its charge is balanced, its electrons settled in its lowest orbit, is far more selective. Most photons simply pass through it, the way light passes through clear glass. The atom is there, but it does not interfere. It does not scatter or redirect. It simply lets the light go by. So as more and more neutral atoms formed, as the electron population shifted from free and reactive to bound and quiet, the universe became, patch by patch, region by region, progressively more transparent. The fog was lifting, not in one place but everywhere, simultaneously, across the entire cosmos. Imagine standing in that infinite, glowing fog, and watching it thin, the light around you, which had always been a wall. A blinding, impenetrable wall of scattered radiance begins to resolve into something you can almost see through. Then something you can see through. Then, all at once, a clarity so complete that you could look outward and see forever in every direction, an unbounded view across the whole of the newly transparent universe. This is the moment that cosmologists sometimes call the surface of last scattering. It is a phrase worth sitting with, because it carries something poetic inside its technical language. Every photon that existed in the universe at that moment had, at some point, its final collision. After that last collision, the electron it had struck settled into an atom, and the photon was released. Free, for the first time, to travel in a straight line. And it has been traveling ever since. Think about what that means. A photon released in that clearing, that first moment of transparency, has been moving through space continuously since the universe was only 380,000 years old. It has not stopped. It has not bounced or scattered or been absorbed. It has simply gone outward in one direction through the expanding universe for more than 13 billion years. Some of those photons have been traveling toward what would eventually become the Milky Way, toward what would eventually become the solar system, toward what would eventually become the Earth, toward the instruments that humans in the last few decades have been careful and patient enough to build. And they are arriving. Right now, tonight, they are arriving. The oldest light in the universe, released in that first moment of clarity, is still coming in. There is something else about this light that is worth holding gently. When it was released, it was warm. The universe at the moment of that clearing was roughly 3,000 degrees. Not the violent heat of earlier times, but still a warmth that would have registered as a deep, glowing orange if any eye had been there to see it. The entire sky, in every direction, would have appeared as a uniform, softly glowing surface, like the inside of an enormous kiln. But the universe has continued expanding since that moment, and as it expands, the light traveling through it is stretched. The wavelength of each photon grows longer, the way a sound wave would be stretched if you were moving away from its source very quickly. Longer wavelengths mean lower energy, cooler light. Over the course of 13 billion years of expansion, that warm orange glow has been stretched so far that it now falls entirely outside the range our eyes can detect. It has become microwave radiation, a form of light that is real and present and measurable, but invisible to us without instruments. The entire sky, right now, is filled with this ancient light, not concentrated in one place, not coming from any particular direction, coming from everywhere, equally, because everywhere in the early universe was the source. Every direction you point a sensitive enough detector, you find the same faint warmth, the same ancient glow, the same light from that first clearing, stretched and cooled by billions of years of travel, arriving still. It took a long time for anyone to find it. And the way it was found is a story in itself. In the spring of 1964, in Crawford Hill, New Jersey, two engineers were having a problem they could not solve. Their names were Arno Penzias and Robert Wilson, and they worked at a research laboratory that had, over the years, been involved in the development of communications technology, satellites, telephone systems, the infrastructure of modern connection. They were careful, methodical, patient people, which is perhaps why what happened to them is so fitting. They had been assigned to work with a large antenna, not a conventional dish-shaped antenna, but something that looked more like an enormous horn, a wide, flared opening mounted on a rotating base, designed to collect faint signals from the sky with exceptional sensitivity. It had been used for satellite communications experiments, but those experiments were winding down, and Penzias and Wilson had an idea to use the antenna for something more interesting, mapping faint radio emissions from our own galaxy. Before they could do that, they needed to understand every source of noise their instrument might pick up. Any good measurement requires knowing your background, knowing what your equipment is producing on its own, separate from whatever you are trying to detect. So they set about characterizing the antenna's noise floor, which is simply the level of random signal that exists even when you are not pointing at anything interesting. And they found something they could not account for. A persistent, low-level hiss, a faint, steady signal arriving from no particular direction. They pointed the antenna at the sky. They pointed it away from the plane of the Milky Way, away from any known source of radio emission. They pointed it at different parts of the sky at different times of day. The hiss remained unchanged, equally present in every direction, at every hour, in every season. It did not vary. It did not strengthen or weaken. It simply was, constant and quiet and maddeningly unexplained. They checked their equipment thoroughly. They looked for problems in the electronics, for sources of interference, for anything that might explain the signal. They considered whether the antenna itself was the problem. And then they noticed something inside the horn. A pair of pigeons had taken up residence there, and the interior surfaces were coated in what Wilson would later describe with the careful language of a scientist as a white dielectric material. They removed the pigeons. They cleaned the antenna. What Penzias and Wilson did not know, as they puzzled over their inexplicable signal, was that a group of physicists at Princeton University, less than 50 miles away, had spent years looking for exactly this. A team led by a physicist named Robert Dicker had reasoned, from the theory of the Big Bang, that if the early universe had been as hot as the theory required, there should be a remnant glow, a faint, cool radiation filling the entire sky, the leftover warmth of that ancient clearing. Dickey's team had actually begun building their own detector to search for it. They were too late. Word reached Princeton that 2 engineers in New Jersey had found an unexplained hiss of exactly the right temperature coming from exactly every direction in the sky. Penzias and Wilson had stumbled into the most ancient light in the universe without knowing that anyone had predicted it, without knowing what they were looking at, while trying to clean a telephone antenna in the New Jersey countryside. The 2 groups met. The pieces fit together. The hiss was the cosmic microwave background, the echo of the universe's first moment of transparency, now cooled to just a few degrees above the coldest possible temperature, arriving at the horn antenna in Crawford Hill as it had been arriving everywhere on Earth for the entirety of human history, unnoticed until 2 patient men refused to accept an unexplained noise. There is something quietly moving about this, if you let yourself feel it. The oldest light in the universe, present in every room you have ever been in, passing through every wall of every house, through the trees, through the air, through you, and utterly invisible, utterly silent to ordinary perception. It had been there on the night you were born. It had been there during every sleep of your life. It had been arriving since long before the Earth existed, and it will keep arriving long after. Penzias and Wilson were awarded the Nobel Prize for Physics in 1978. Their discovery did not just confirm the Big Bang theory over its rivals, it opened a door onto something much richer, the faint patterns hidden within that ancient glow, patterns that would turn out to be the seeds of everything. The light Penzias and Wilson found was, to the instruments of their time, essentially uniform, the same temperature, in every direction, to within the precision they could measure. And for a while, that uniformity was itself the message. Here is the echo of the Big Bang. Here is the proof of an early universe hot enough to produce this glow. Here is the confirmation that the theory is right. But the universe, as it turned out, was not perfectly smooth. Not quite. Hiding within that ancient light, far below the precision of the original discovery, were tiny variations, patches of sky that were the faintest fraction of a degree warmer than their neighbors. Other patches, the faintest fraction of a degree cooler. The differences were so small, roughly 1 part in 100,000, that detecting them required instruments of extraordinary sensitivity, instruments that did not exist in 1964 and would not exist for decades. To put that scale in some kind of perspective, if the average temperature of the cosmic background light is represented by a wall painted a single color, the variations are the difference between 2 shades of that color so similar that you would need to hold them side by side in perfect light to see any difference at all. Smaller than that even. They are almost not there. Almost. But they are there, and they are everything. Those tiny variations, those faint ripples in the ancient light, are the fingerprints of the early universe's structure. Before recombination, the plasma filling the universe was not perfectly uniform either. There were regions that were very slightly denser than their surroundings, and regions that were very slightly less dense. The differences were tiny, but they were real, and they left their mark on the light. Here is how, in the denser regions of the plasma, the particles were slightly more compressed. Compressed things are slightly hotter. Slightly hotter regions left a slightly warmer imprint on the photons that were released when those regions became transparent. In the slightly emptier regions, the reverse was true. A hair cooler, a hair dimmer. When the fog cleared and the photons set off on their journeys, they carried this information with them. Encoded in their temperatures, invisible and patient, was a map of the universe's density at the moment of that first clearing. The slightly denser regions, over the following billions of years, pulled in more matter through gravity. Slowly, over enormous spans of time, those small overdensities grew. They attracted hydrogen and helium and accumulated more mass, which attracted more mass still, which grew and condensed and eventually, after hundreds of millions of years, ignited into the first stars. The stars gathered into galaxies. The galaxies gathered into clusters. The clusters gathered into the vast web-like architecture of the universe as it exists today. enormous filaments of galaxies stretching across billions of light-years with vast empty voids between them. All of that structure, all of that architecture, all of those galaxies and clusters and the very existence of the Earth and everything on it, it all traces back to those tiny ripples in the ancient light. The seeds were there, in the plasma, before any atom had formed. The clearing revealed them, and the light has been carrying their record ever since. The effort to map those ripples in detail became one of the great scientific projects of the late 20th and early 21st centuries. A series of satellite missions were built with the sole purpose of measuring the temperature of the cosmic background light across the entire sky, with greater and greater precision. The most detailed of these, at least until recently, was a telescope called Planck, named not for its purpose, but in the tradition of honoring a physicist, though we can set the name aside and simply call it what it was, an extraordinarily sensitive thermometer in space, placed far from Earth to avoid the warmth of our planet interfering with its measurements, scanning the whole sky for years and building up a picture of the ancient glow in finer detail than had ever been achieved with the R. The map it produced is genuinely called, by the scientists who study it, a baby picture of the universe. Not metaphorically. That is the phrase they use, because it is accurate. This is the earliest image we have of the cosmos, a portrait taken when everything was less than 400,000 years old. The mottled pattern of slightly warmer and slightly cooler patches is the face of the infant universe, and it is extraordinarily close to what the standard picture of cosmology predicted it would look like. Extraordinarily close, but not perfectly matching. And in the small, quiet places where the map and the prediction diverge, there are questions that remain open. Questions that, if you are lying in the dark tonight, you do not need to worry about, but that are worth knowing exist because they are the edges of what we understand, and edges are where the most interesting things tend to live. In the southern part of the sky, there is a region. It is not visible to the eye, of course. This is a feature in the microwave background light, detectable only by the most sensitive instruments, but it is there, and it has been seen by multiple telescopes, mapped by multiple missions, confirmed by researchers working independently of one another. It is larger than it should be, cooler than its surroundings by a margin that is small in absolute terms, but large by the standards of a background that is otherwise almost perfectly uniform. It is called, simply, the cold spot. When it was first clearly identified in data from a sky survey in the early 2000s, the immediate question was whether it was real, whether it was a genuine feature of the ancient light or an artifact of the instruments, a shadow cast by something between us and the cosmic background. Further investigation confirmed that it is real. The cold spot is genuinely there, genuinely unusual, genuinely not quite explained by the standard picture of how the early universe should look. The most straightforward explanation that was proposed, and it is a reasonable one, worth following, is that between us and the cold spot, there might be an unusually large and deep void in the distribution of galaxies, a supervoid, as it has been called, a region of space that contains significantly less matter than average, a kind of cosmic hollow. Light passing through such a hollow loses a little energy on the way through, in a process related to how the expansion of the universe affects photons as they travel. If the void is large enough and deep enough, the light reaching us from that direction might appear slightly cooler, producing exactly the kind of feature we see. Researchers have searched for this supervoid. Something has been found, a large, underdense region in the right general direction. But when the numbers are worked through carefully, the supervoid that exists does not seem to be quite large enough or quite empty enough to account for the full extent of the cold spot's chill. A study published in 2025, which brought together multiple lines of evidence, including the distribution of galaxies and the way the background light has been gently bent by the gravity of large-scale structure, concluded that the supervoid alone cannot be the complete explanation. What else might explain it? Researchers have proposed several possibilities, each more speculative than the last. There could be features in the very early universe, patterns set down before recombination, perhaps during the period of rapid expansion thought to have occurred in the first fraction of a second, that left an unusually cold imprint in one region of the sky. There could be something about the geometry or topology of the universe on very large scales that produces such features. There are even proposals, offered tentatively and with appropriate caution, that the cold spot might be a trace of a collision, an interaction in the universe's earliest moments between our region of space and another region that is now causally separate from us, forever beyond the horizon of what we can observe. A neighboring universe in some formulations of how the cosmos might be structured. This last idea is offered here not as a conclusion, but as a question, one of many questions that the ancient light has raised without yet answering. The cold spot is not the only place where the cosmic background map and the standard predictions do not quite agree. There is a large-scale feature, the way the temperature varies across the very biggest scales in the sky, that comes out weaker than expected, at a level that has been measured and confirmed but not explained. There are hints of an alignment between large-scale features that, if the universe is truly random and isotropic in every direction as the standard picture assumes, should not be aligned at all. None of these anomalies are large. None of them overturn the standard picture, which fits the cosmic background data extraordinarily well in almost every respect. But they persist. They have been seen in the data from multiple independent missions. They have been examined and re-examined, and they have not gone away. There is also a separate tension, quieter but perhaps more significant in its implications. When cosmologists measure how fast the universe is currently expanding, they get one answer. When they calculate what the expansion rate should be, based on the properties of the cosmic background light and the standard picture of the universe's history, they get a slightly different answer. Not wildly different, but consistently, stubbornly different, in a way that has become more pronounced as measurements have grown more precise. Two careful methods, both well-founded, arriving at slightly different conclusions. Something in our understanding, somewhere, may be incomplete. These are the edges of what we know, not failures. The standard picture is a remarkable achievement, a framework that explains an enormous range of observations with extraordinary precision, but the edges are there, and they are honest. They are the places where the map of our understanding has been drawn as far as the data allows, and then the line stops, and beyond the line there is simply the open, patient, uncharted territory of what we have not yet figured out. The universe, it turns out, keeps its own counsel. It offers us the ancient light and lets us read what we can from it. It does not explain the cold spot. It holds its anomalies quietly, the way deep water holds things that have sunk into it. Present, real, waiting for the right kind of attention. There is something restful in that, if you let it be. The universe does not require us to have all the answers tonight. The questions can wait. They have been waiting in the light for more than 13 billion years. Every atom in your body has a history that reaches back to that first clearing. Not metaphorically, not in the loose sense of deep connection that we sometimes reach for when we want to feel part of something larger. Literally, the protons at the heart of the atoms in your hands, your breath, the slow weight of your body resting now. Those protons were present in the plasma of the early universe. They were there, in the heat, waiting through 400,000 years for the temperature to fall. They were part of the fog. They were among the countless billions of particles that, when the moment finally came, found their electrons and settled into the first hydrogen atoms. Most of the hydrogen that formed in that first clearing has had a long life since. It drifted through the dark ages that followed, the long period after recombination when the universe was transparent, but empty of stars, when the only light was the fading glow of the background radiation and there were no new sources to replace it. Then gravity slowly gathered the hydrogen into clouds, the clouds into denser concentrations, the densest concentrations into the first stars, enormous, brief, brilliant objects that burned through their fuel and scattered their matter back into space. New generations of stars formed from that scattered matter, and in the furnaces of those stars, heavier atoms were built: carbon, oxygen, nitrogen, iron, the atoms that make complex chemistry possible, the atoms that make life possible. Some of that matter, after many generations of stars, found its way into a cloud that collapsed to form a small star and its orbiting planets. On one of those planets, under conditions that remain only partially understood, the chemistry became self-replicating. And here, after all of that, after all that time and all those transformations, you are lying quietly, breathing slowly, made entirely of material that was once a free particle in the early universe's fog. The cosmic background light is not a historical artifact. It is not something that happened and is now finished. It is happening now. Those ancient photons, released in the moment of the first clearing, are still traveling. They are passing through the walls of this room right now. They are passing through you, as they have done every moment of your life, and every moment before your life, and every moment before the earth existed to have a surface for them to pass through. There is a quality to this that is difficult to name. Not quite wonder, though it is that, and not quite comfort, though it is that too. Something more like recognition. The sense that the universe is not a distant thing, not an abstraction or a backdrop, but something present and immediate. Something that has been with you, in the most literal physical sense, since before you were born. The Planck telescope, floating in space far from Earth, mapped those photons with extraordinary care. It spent years turning its sensitive instruments toward the sky, building up its picture of the ancient light one careful measurement at a time. The image it produced, that mottled, softly varied map of the oldest thing we can see, is sometimes described as the most important picture ever taken. And there is a sense in which that is true. It is a picture of the moment the universe first became itself, in the form we recognize, the moment it went from opaque to transparent, from formless to structured, from a place where light could not travel to a place where it could. That moment was not a dramatic one by the standards of what had come before. No explosion, no sudden rupture, just a slow, patient cooling, reaching a threshold, and then, quietly, everywhere at once, the fog lifting. It is a long way from that first moment of transparency to tonight. 13 billion years and more. Stars have been born and died in their billions. Galaxies have assembled and merged and evolved. The universe has grown so vast that the distances between things are almost beyond any useful imagining. And through all of it, those photons have been traveling, not hurrying, not fading, just going steadily and without interruption through the expanding dark. Some of them, the ones that have been traveling in the direction of this small planet, have been arriving here for as long as Earth has existed. They pass through the atmosphere of a world without life. They pass through skies above the first simple organisms. They pass through air breathed by creatures whose names we will never know. They were present on every night that every human being who has ever lived looked up at the sky and wondered what was out there. And tonight they are arriving here, in the room where you are resting, passing through you as they pass through everything, carrying their ancient information, their record of that first clearing, their long, patient memory of the moment the universe became transparent and the light went free. You do not need to hold on to that. You do not need to carry it anywhere. The light has been carrying itself for long enough. It knows the way. Your body is heavy now, and the day is somewhere very far behind you. The atoms that make you up have been on a long journey, longer than any story, longer than any sleep, and tonight they are resting. As the universe, in its own way, is always resting and always moving at once, patient and vast and unhurried. The ancient light comes in through the walls, The atoms in the pillow and the atoms in your hands were once free in the same deep fog. The protons in your breath were there, in the plasma, before the first atom had ever formed. You are made of the universe's first matter. And somewhere, very distant now, the day is already fading into something quieter than quiet. Drift now, if you are ready. Sleep well,